Hello everyone. Now that we have a sense of how to find the derivative using different rules of derivatives, we can move to the graphical applications of the derivative. So we can use this information to know the highest and lowest points of a function, and uh, we can figure out a rough sketch of a function, like what does a function look like. So if you want to get a feel of a function, so first thing we need is to find where the roots of the function are. So for example, let's take a look at this graph. So this curve cut, cuts the x-axis at these points. So 1, 2, 3, 4, 5. So clearly these are the values, x values where the function's value is 0. And then similarly, we can find the maxima and minimum points. For that, we're going to use our information of the slope. So maximum and minimum points are the points where slope is 0. Because if you draw a tangent line at any maxima or minima point, so it can be a local maxima or it can be an absolute maxima or local minima or absolute minima. So soon I'll talk about those definitions. But for now, like if we want to find a maximum minimum point, we see where the slope is 0. And we can also get some information about the other interesting points on the curve. For example, if second derivative is 0 at some point, so that might be a possible inflection point. And what does inflection point mean? So it means that the concavity of the curve changes. Concavity changes. And now you're going to ask me, what is concavity? So the curve is called concave up if it looks like this, concave up. And if it looks like this, that is called concave down. So wherever it goes from concave up to concave down or concave down to concave up, so wherever concavity changes, those points are called inflection points. So if we'll just take a look at the curve here, so we can suspect that, so it was concave down, then after this point, so where we have the maximum slope, so it becomes concave up, so this might be a possible inflection point, or this might be a possible inflection point, or somewhere here we might have a possible inflection point. So we can just get a gist of like a look feel of the function if we know some things about the function. So our differentiation helps us in curve sketching as well. We move on to the curve sketching, I'm going to discuss the terminology that we're going to use for local maxima, local minima, absolute maxima, etc. And also I'm going to discuss our first derivative test in this video. All right, so let's discuss the terminology. So stationary points or critical values are the points that have a horizontal tangent or where the slope is 0. So then we're going to talk about the maximum and minimum points. So for the maximum or the higher points, we're going to use the word peak. And for lower points, we're going to use the word valley. So you can just think about the mountains and the valleys. So maximum point are the critical values located at peak. So critical values located at peaks. Minimum points are the critical values located at, so opposite of peak is valleys. And absolute maximum would be the highest peak, and absolute minimum would be the lowest valley. So as the name suggests, so lowest of all, so absolute minima of all, and relative maximum will be all other peaks. So it can be the all other smaller peaks, all other peaks. Similarly, relative minima would be all other valleys. So now let's discuss this in context of a diagram. So if we look at the curve on the left. And let's say we are working with this domain -2 to 2. So first of all, if I ask you to find all the roots, so roots are where it crosses the x-axis. So these are our roots of the function. So if I ask you to find the absolute maxima in the domain of -2 to 2, so absolute maxima will be at the point A. So absolute maxima is at point A. So if I ask you to find absolute minima, so that would be the lowest of all the values, that is point D. And if I say just find uh, all the maximas and minima, so we can see that C is also a maxima and B is also a minima. So that would be our relative maxima and relative minima. And if we restrict the domain, so if we restrict the domain -1 to 1, so in that domain, your absolute maximum would be C, so it will change, and absolute minima would be B. Absolute minimum would be B. So now I want to do a bit of discussion about how the value of the derivative and the behavior of the function, they are related to each other. So based on the value of the slope, whether it's positive or negative, we can tell whether a function is increasing or decreasing in that interval. So let's start from here. So let's take a look at this diagram. So here, if I take the slope of tangent at each point, so what we notice? So we notice that the slope is positive. So it means when the slope is positive, and also after this point, so here at the maximum height, so it reaches 0, so slope becomes 0. And then after this point, if we talk about the slope, it becomes negative. So when slope is positive, the function is increasing. When the slope becomes negative, the function is decreased. So it's decreasing. So thus we say that in this one, so fx is increasing, and then in this interval, fx is decreasing. And in other words, it looks something like this. So it means here function is concave down. Similarly, if we talk about the next bit from here, so function, the slope is negative, and then after this point, the slope again starts being positive. So in that case, so if you just draw the line, you can see that so slope is positive. So again, in this interval, the slope is positive, and the function reaches the maximum height, and the slope becomes 0. And again, after this point, the slope becomes negative. Again, so whenever the slope is positive, we notice that the function is increasing. Whenever the slope is negative, we notice that the function is decreasing. And it means in this interval, so we have something like, so here we had, so decreasing to increasing, and then increasing to decreasing. And again, in the last bit, after attaining the horizontal slope, it again becomes positive, and it means the function again starts increasing. So it looks something like this. So here we all see that at all these points, whenever in the interval slope is positive, the function is increasing. When the slope is negative, the function is decreasing. So the sign of the slope tells you whether you get increasing function or decreasing function. And there is another information that we can derive from here. So all these points are the critical points where we have the dashed line, because at these points the slope is 0, and in the neighborhood, if the function change from increasing to decreasing or the slope changes from positive to negative, we get a point of, so this would be a point of maxima. When it goes from negative to positive, then we get a point of minima. Again, point of maxima, point of minima. Thus, we make few observations from this discussion. So I'm going to just write our observations here. And another thing is these critical points, these points of maxima or minima are called the critical point. So this is a point x value where we attain a maxima or minima. So these are our critical point. So we get that the critical values separate the function into regions from where fx is increasing to where fx is decreasing. So critical values separate the increasing part of the function from the decreasing part of the function. So now we're going to discuss our first derivative test in which we're going to use this information. So a first derivative test is a means for investigating either side of a critical value. So there are four possibilities. So the case one, when we have a local maxima. So it means what we have here is, so we have a critical value and we notice that, so the value, the slope here, so slope at critical value is 0 because we have a horizontal tangent here. All right, so now we're going to do some observation around the critical point in the neighborhood of the critical point. So if we look at the left side of the critical point and we draw the tangents to the curve, these should be tangents, and we notice that all the slopes are positive. So on this side, all slopes positive. Similarly, on the other side, if we draw and we notice that, so all the slopes are negative. So all the slopes are negative. So basically we are looking in the left side and in the right side of the critical point. So I'm going to make my table here. So I'm going to choose some test points. So here is in the middle is my critical value. And if I look at the x values on the left of the critical value, I notice that the slope is always positive. So positive slope means the function is increasing. Similarly, if I look at the right side of the critical value, so for all the x's which are greater than critical value, the slopes are negative. It means the function is decreasing in that interval. So from here, what we can conclude, conclude is that curve changes behavior like this from increasing to decreasing. So this critical value is a point of local maxima. So we call that it's a point of maxima. So function will attain a local maximum value at this critical point xcv. So fxcv will be that value. So point of local maxima would be this. Similarly, we can discuss our next case. So next we have, so if we have something like this, again, we're going to do the same thing. First, we're going to look at our critical value. So this is our xcv. And then we're going to look in the neighborhood of this critical value. So if we look in the left, so we see that, so we have the negative slope. So all slopes negative. If we look on the right hand side, so we notice that, so all slopes positive, and we can create a similar table as before. So on the left hand side of critical value, so all the slopes are negative. It means the function is decreasing. On the right hand side of the critical value, all the slopes are positive. It means the function is increasing. And we get something like this. The curve is like this. So this tells us that here we have a point of local minima. So local minima would happen at x, this critical value, and that point would be xcv and the value of the function at that point. So if the sign of slope changes from negative to positive in the neighborhood of critical value, we get a local minima. It's always a good idea to make the table and draw it so that you don't confuse like positive to negative versus negative to positive. Or we can have something like this. So where our critical point, so slope is 0 here. So this is our critical point. And if we look at the left hand side of the critical point, so we see that the slope is all slopes are positive on the left hand side, and similarly if we look at the right hand side of the critical value, again all slopes are positive. So slope is not changing its sign, and slope is 0 here at the critical point. So in that case, again if we make our table, so we notice that slope remains positive. It means the function is increasing. Again, it remains positive on the right hand side. Function is increasing. So that is called, that critical value is called inflection point. Inflection point. So it's neither a local minima nor a local maxima. It's a inflection point. So slope continuously keeps on increasing. Then we get inflection point. So let's discuss our last and the fourth case. So if we have something like this again, so our slope is going to be 0 at this point. So this is our critical point. And if we look in the left of this critical point, we see that all slopes are negative. Similarly, on the other side, again, all slopes negative. Again, the slope is not changing its sign in the neighborhood of critical value. So then we get inflection point again. Thus, we again get an inflection point. And remember, inflection point is the point where the curve changes its concavity. So here the slopes are always decreasing. So overall, the gist of this discussion is if the slopes change sign around the critical value from left to right, then we have a point of maxima or point of minima, or in other words, an extreme point. But if slopes do not change, then we have inflection point as our critical point. I hope that makes sense. In the next video, I will show you some application problems of first derivative test. Thanks for watching.